hit by mu times n. So this is going to be our limitation on the angle theta. So we can see all of this in a Mathematica file. Let me bring it up so that it's a little bit clearer via graphs. So I put the file here. Let me save it in the right spot. I need to save all of it from here, certainly. So let me change the screen environment, presentation, so it's turn off the lights. So what we have here are the values that were given to us, the velocity, 30 feet per second, g, m, and so on. And here you find the normal force. So it was this, you see W cosine theta, and I'm using theta in degrees, so that's why I'm writing that degree, because Mathematica is by default in radians, plus mv squared sine theta over rho. So this is what we have here. So this is the normal force. Now this is the friction force. So when I was doing it here, I took the friction force in the opposite direction. And that's why I got the opposite of that, but it doesn't really matter. So we have mg sine theta minus mv squared over rho cosine theta. So what I'm asking is to plot the friction force, to plot mu times the normal force, and minus mu times the normal force. So this is mu times the normal force, and this is minus mu times the normal force. So the friction force should be always between these two values. And we see that it doesn't always work. What we have here is so the value of the forces versus the angle. So for a velocity of 30 feet per second, the friction force that would be needed to have equilibrium with an angle of, let's say, 20 degrees would be here. But that friction force is not available because it is in absolute value more than mu times m. So here, the person would fly off the cushion. And it's only for a theta that is beyond this value that the person can stay on the cushion. So then you can ask Mathematica to solve for that angle, and you find that it is 47 degrees. So if the cushion is bent less than 47 degrees, so if it is more horizontal than 47 degrees, the person will fly off. And here, there is no intersection between this and that, so there is no maximum value of theta. So you can go, the person can be vertical, the person still stays on the cushion.
As long as it's going that velocity.
Right. So, of course, if you were to decrease the velocity, you would expect that there is also a maximum value of theta for this. And something that you can ask Mathematica to do. So that's the second part here. So what I'm doing here, I'm clearing the variable v. And I'm plotting the same thing. So we have the friction force, the normal times mu, and the normal minus the times minus mu. I'm asking for this between 0 and 90 degrees, and I'm using the command manipulate. So v is parameters that can vary between 0 and 50. And by having the slider here move around, I can change the value of v. So let's see what this gives us. I think I need to activate also what is here to get all of these values updated. So see here we have a v of 0. You can see the value if I expand that. So for a v of 0, so what do we see here? We have mu times n minus mu times n on the friction force. So, well, for a v of 0, there's no rotation. So it's a static problem. So basically, the question is, well, can the person be in equilibrium just resting on the cushion? So of course, if the cushion is horizontal, no problem. You don't even need any friction force. The normal is enough. But then, at some point, static friction is not going to be enough. So it's basically this problem, you see. This is a person, this is a cushion, there's no rotation, and you ask, when is a person going to sleep? So that's what is happening. And so it is at this angle. But now, let's increase the velocity. So let me increase the velocity. You see that the curves change a little bit. So with velocity, when the person is horizontal, still possible to be in equilibrium, no problem. And now you can go to an angle that's a bit larger for the cushion. But at some point, this curve will intersect minus mu n.
So as you get towards the bottom curve, you're afraid of slipping up?
So yeah, what are these two positions? So these 2 points here, they correspond to a theta mean and a theta max. So theta mean would mean you slip away from the cushion. Theta max would mean you would slip down. So there is no enough friction to hold you up, and here there is not enough friction to hold you in. So here what we have, if the person is too horizontal, the person will slip out. And if the person is too vertical, the person will slip down. And in this range, it's okay. And what we had, you see here, the velocity is 15. And at some point, the person will be okay, whatever the value of the angle is for the, let me rephrase that. If, so at some point, if I increase V, this curve will no longer intersect the friction curve, so meaning that the person cannot fall down anymore. The person can only slip out of the cushion. So you get this, if you increase it, you see at some point here. After that, you're always okay, you never slip down. But of course, here, you cannot be too horizontal because then you would slip out. So it's interesting what is happening.
Why is the blue line changing shape?
It's because it is a friction force and it depends on the velocity.
Oh.
So it's like a parabola, V squared. So that's why if V is changing of value, well, it's not the same value. It has to change because you know, the friction force is dependent on the velocity that you have. You're asking what kind of, how much friction do I need for a given angle on a given velocity? So of course, if you change the velocity, your friction force will change. It comes from here, just this formula.
I see. So the blue line is the friction.
Right, so let me rephrase that. The blue line is the friction force. This is the range you can have for a certain angle. So at 20 degrees, the static friction that you have available is anywhere between here and here. Because this is mu times n, and this is minus mu times n. So this is what you have physically available. Now your computation is telling you at 20 degrees to stay in equilibrium, you need that. You cannot have it. So then the person will slip off the cushion. Okay.
It's a little bit related to topic. Does static friction have potential